Hello everyone, welcome to lecture number 8, and in this lecture we are going to continue first with the nomenclature that for the Adlayers. So, you remember last class we have actually just familiarized something called Wood's notation, and now I will actually take you to another type of notation which is actually known as metric notation, which is of course a more methodical and systematic method that is commonly used. And then we will look at something called real Adlayers and something called superlattices, due to the fact that not all atoms are necessarily adsorbing on the same side. You can actually have something called superlattice, and then finally we will also just familiarize the different general classification of the Adlayer lattices. All right. So, now let us look at the metric notation, but before that let me just show you these two examples here. So, this is like an FCC 111 surface, where this is the surface atom and the blue or the gray atoms are actually the ad atoms or the Adlayer in general, right. So, the interesting thing, when you look at this Adlayer, so both of them are looking same ideally, and if you would write down the Wood's notation of both of them, you would write down it is to be 1 by 2 or 1 by 2, because you can see that the Adlayer lattice is basically 2 times that of the surface lattice along one direction, and along the other direction it is exactly same as that of the surface unit lattice vector. So, that means it is actually 1 by 2 Adlayer, and both the names are basically the same. But now the interesting thing, if you look carefully, the Wood's notations are the same, but the Adlayers are not the same. You can see that there is truly a difference in the symmetry of the Adlayer with respect to the surface. You can see here the oblique of this particular Adlayer is basically facing to this side, and the oblique of this Adlayer is basically facing to this side. So, ideally these two are just nothing but mirror Adlayers, but that is not reflected in the Wood's notation. So, the Wood's notation is basically not representing the real symmetry of the Adlayer. So, that is the reason why we need to now look for another type of notation, which is basically a clearer and a more methodical type of notation, which is actually known as the metric notation. So, how do we do that? It is very simple. Again, what we are going to write down, or we are going to write down a small mathematical expression for the unit lattice vector of the Adlayer in terms of the two unit lattice vectors of the surface itself, yeah, and they will be connected using two integers, and the integers particularly along the direction of the Adlayer lattice, and that is the reason why you would find this is actually called as M1 and this is actually called as M12, and here you have an M22 and then here you have an M21. That is a connection basically. You will see that now when I do an example. So, let us try to do that for this particular example. So, this you remember was a 1 by 1 supercell of an FCC 100 surface. Now, well then finally, if I would write down, so I can basically just represent my B1 and B2, that is actually the Adlayer unit lattice vectors in terms of the surface unit lattice vectors using a metric. That is the point. Now, let us do that. So, for example, if I want to write down B1, you can see that B1 is actually 1 time A1, 1 time A1 and 0 times A2, and that is the first equation to represent the B1. And for B2, it is basically 0 times A1 and then it is plus 1 time A2. Now, I can write down the metric is basically a 1001. So, that means the surface can actually be named as FCC 100, that is the surface, and this is basically the metric notation corresponding to this particular Adlayer. Well, here it is not huge surprising, but you can now see for more complex surfaces you will see that it is actually becoming more interesting. Now, let us look at this one. This is basically a 2 by 1 super hard layer. Now, if I want to write down the metric notation, I have to express basically the unit lattice vector of the hard layer B1 in terms of A1 and A2. So, this is basically 1 A1 plus 0 A2, and B2 is basically 0 A2 and 2 A2. So, that means the metric is basically 1 0 0 2, and then I can write down the expression or the name of the surface as FCC 1 0 0, then 1 0 0 2. Yeah, the 1 and 2 is actually telling you it is a 1 by 2, or in this the 1 and 1 basically telling it is a 1 by 1. So, for these ones it is very simple. But let us look at more examples, but before that the general expression is basically that you have to write down the surface, then you have to write down whether it is a centered or primitive, and then you have to also basically write down the metric notation, and then finally the adsorbate atom. Good. So, let us assume this particular hard layer. So, the blue is again basically the hard layer, and this is basically the surface. And now, we can check what is actually the metric representation for the blue and for this magenta unit cells or primitive cells that we have actually just representing this particular hard layer. Now, let us look at this. So, you can basically see here that the B1 of this one can actually be represented. So, you can see that the B1 is actually 1 time A1 and minus A2, 1 time minus A2. So, that means you move along A1 once and then you actually go in the negative direction along A2, then you would reach at B1. So, yeah, that is basically the representation, and then for B2 it is basically 1 time A1 and then positive it is actually 1 time A2. So, you would get 1 A1 and 1 A2. So, that means the metric notation is basically 1 minus 1 1 1. So, the surface can actually be called as FCC 1 0 0 1 minus 1 1 1. Now, for the blue how does it look like? The blue would look like this, where you basically have a 2 by 2 metric that you are obtaining, but here you see this is basically a centered, this is a centered cell, not a primitive cell. So, therefore, you would call this one as FCC 1 0 0, then you write down the C for the centered, for primitive you do not write it, and then the metric notation is basically the 2 0 0 2, or it is a 2 by 2 cell. So, that is basically it. Now, during the assignment time, we will basically just give you more assignments to work out, and then you can basically solve more complex hard layer, and you can get familiarized with these kind of notations, both the Woods notation and the metric notation. Now, before we go into look into the real hard layers, let me just also introduce something to you called as coverage. What is the meaning of coverage? Coverage is something that you would use now to basically just see how dense is the adsorbate atoms on the surface. You remember we have actually familiarized something called the packing density for the surface atoms density. Similarly, for the surface for the coverage or for the density of the concentration of the hard layer atoms, we want to basically just represent it something called coverage. How can we define the coverage? So, coverage is basically defined by something called the number of atoms in the hard layer unit cell. So, now you see here this is my surface, and the magenta is basically my hard atoms or hard layer. Now, you can see the unit cell of the hard layer is basically this one, and how many atoms are present in that hard layer? So, I have basically 1 atom in this cell, and then I have to calculate basically the number of atoms of the surface in the hard layer unit cell. Yeah. So, that means I have to basically check how many atoms are there from the surface which is actually occupying the area of the hard layer lattice. Now, you can see that this is just one atom is occupying the area of the Adlayer lattice from the surface. So, that means for this particular case the density or the coverage is 1 by 1, that means it is actually a 1 monolayer. A 1 monolayer, or typically ml, is actually the unit for this, it is actually called as monolayer, and 1 monolayer represent that the surface is completely covered, or meaning that every single surface atom is actually occupying one Adlayer atom. Now, let us look at another surface. So, this is another surface which is a less dense surface, you clearly see that. Now, this is the unit cell of your surface, the Adlayer, and now you can clearly see that I have one atom in the Adlayer lattice, but you can see I have 4 atoms in the surface, 1, 2, 3, 4 atoms in the surface, right. For the Adlayer I have basically 1 here and 1 here. So, total I have 2 atoms. So, that means 1 plus this one, so which is actually equal to 2. So, that means if I now would calculate the density or the coverage, you basically have 2 by 4, and that is actually something called a half monolayer. That means this actually meaning that the surface is half occupied by the Adlayer atoms. Or you can actually have a extremely dense layer where you see now that it is the same as the first case, but now I have an extra atom which is sitting in the middle of the Adlayer lattice, which is making that the density to be 2 by 1, that means it is actually 2 monolayer. But this is an extremely odd situation, this is not common, this situation is not very common, but I just for the understanding I have basically just given you, you can basically calculate the coverage or the density of the Adlayer atoms using this particular method. Well, now look at the real Adlayers. So far what I have shown you in the all examples, I have always tried to stick an adsorbate atom, add atoms on the top or the so called atope position of the surface. It is not true all the time, because we have already seen in the possible adsorption sites that there are, depending on the surface that is offered, I can actually have different type of adsorption sites. So, why did I do that all the time? It is just for convenience I did it, but just believe me that the same Adlayer can actually be represented also by occupying them equally at an HCP or FCC site or at bridge site. So, here I have an add atom at the atope sites, here at the HCP or FCC site, and here at the bridge site. So, all possibilities are there. But now the question that you would ask, are they different? No, they are not different, they are all the same, they will all be like a 1 by 2 supercell, as you would imagine. But the point what I want to make is, depending on the atom or depending on the reactivity or whatsoever factor that you would find out, the atoms can actually occupy this variety of positions, and it is not also necessary that all the time every atom would occupy on the same site, it may also occupy on variety of sites. You will see that in the other examples. Here I have one more example from an FCC 100 surface. There you also see that atoms occupying the atope site, the atoms occupying the bridge site, or the atoms occupying the hollow site. Yeah, hollow site. So, they are all same, these are all 1 by 1 supercell. Yeah, so, they are all technically the same, but just occupying the different sites. Now comes the interesting aspect. I want to put one more interesting aspect into the Adlayer, but now when you look at this, very striking in it. Not every atom, as you would mark, are actually just occupying the same site. These things that I am marking are of course occupying an atope site, but this particular atom that I am marking with green color is actually occupying a bridge site. I have a bridge site and here I have an atope site. So, you see that within a one single Adlayer, I am going to get now variety of adsorption sites for the Adlayer atoms, and that giving rise to atoms with variety of adsorption site. Now, something that you have to keep it in mind here particularly, because now when I want to define the unit cell of this particular case, it is not possible to represent using this type of unit cell. because you see now that these atoms here are actually not the same as these atoms. You understand? So, which actually meaning that this cannot be used as a representation for the Adlayer unit cell. So, the only representation that we can use is basically this one. This is correct and this is wrong. It is all because the add atoms are not represented properly using this particular representation. Therefore, you please keep it in mind that when you represent for a real Adlayer, the add atoms that you choose for making the primitive cell or the so called unit cell of the Adlayer, it has to be always with respect to the surface. Well, that is the point what I have just mentioned. Now, let us look at a bit more complex case, where you can see now I have an extremely interesting Adlayer, where not all atoms are actually just occupying the same site. You can see this atom is occupying, of course, the same site. This one, after the 5th atom or after the 4th atom of the Adlayer along the B2 direction, I am basically able to occupy this. So, this truly because when you make an Adlayer, it is not necessary that always you make an Adlayer of one material on the other. It is always different type of material, and their bulk atom distance are different. For example, if I try to make a silver Adlayer on copper, the copper bulk lattice is 2.5 and that of the silver lattice is basically 2.9. You see there is a difference of about 0.4 angstrom mismatch between the copper lattice and the silver lattice. So, that means when you occupy them on the surface, the copper need to relax or the silver need to relax, but this is something what happens at the interface. We will look into that later in special cases, but because of this reason, because of this heteroatomic interfaces that you are creating, it is not necessary that always they go on the same site, right. So, because of that, now you can see that there is actually something that you are forming called as a super lattice. You are actually forming super lattices. That means it is not very simple lattice, the lattice periodicity is actually much bigger. You can see the lattice periodicity, in this case it is B2, which is actually much larger than that of the surface lattice. But now again the point is, please keep it in mind that this is not the representation of the surface. So, this cannot be used, and this is the true representation of the surface, because you need to always consider into atoms that are in registry with the graphates with the surface lattice. Now, the interesting thing about the super lattice is also that due to the fact that the atoms have variety of adsorption site, you can see that they also have a variable height. They are also just changing their height. That means the height is also getting modulated on the Adlayer. So, that means they are not just atomically flat, instead they are slightly modulating their height because of the variety of adsorption site, and that is one example I would like to discuss with you here. This is again an STM topograph of a sulfur Adlayer sticking on copper 110 surface. Well, what you are seeing here, all these bright spots, every bright spots that you are seeing here are nothing but sulfur atoms. These are the sulfur atoms. But now you see that not all sulfur atoms are looking similarly bright, they are looking different. So, the question that you would ask, well, why are they different? Well, then comes the real argument that I have put forward before. The real reason is because not all sulfur atoms are actually occupying the same site. You can see here this corner atom, sulfur atom, is actually occupying the hollow site, but then after that about 8 atoms further. So, that means along this direction, if you count, after 8th atom, this is again occupying the same site. And now these atoms are actually occupying the same site, that means the hollow site, but the atoms that are in between are not occupying the same site, and that is the reason why they are actually appearing different. So, this is actually a true experimental result of a sulfur Adlayer on copper, where you can see this kind of real effect, or this is something called a real Adlayer mostly looking like. And also it depends on the coverage, because at the lower coverage you would find that atoms can occupy a more stable adsorption site, but as the coverage increases, the atoms would start to occupy on a completely compact layer, where you can actually start to observe these kind of real Adlayer. Now, the one more important point that I would like to mention here is actually there is a general classification of Adlayer. If the Adlayer lattice, that means the Adlayer lattice divided by the unit lattice vector of the surface, if they are coming to be like integer numbers like 1, 2, 3 and so on, then you would call this lattice as a commensurate lattice. That means the lattice is actually in commensuration with the surface. But there is another one where you can see the magnitude, this magnitude is actually kind of not really an integer number with in relation to the surface unit lattice vector, but if you are getting something like 1, 1 by 4, half, 3/4, 2 and things like that, then typically you call it as a coincidence lattice. Or if that is absolutely not possible, if this distance is actually kind of a fractional number with respect to that of the surface lattice, then you would basically call it as an incommensurate lattice. And that means it is not really in registry with the surface lattice, and that is typically the surface that you would basically find in this case. This is a general classification, a general name that you would use, and they can also have this modulation. So, you can also form superlattice. And finally, what I want to show you is one more important thing. Although we have actually considered so far only an extremely flat and smooth surfaces, but you see the real experimental result shows this is a silver 111 surface prepared using sputtering and annealing, and after the preparation you find the surface is not looking extremely like flat as we have expected. It is actually looking much more heterogeneous. You would find, for example, monoatomic step edges, you would find vacancies, you would find terraces. Terraces are good, that is exactly what we have expected. You would also find, for example, kings, these are actually small change in the step edges, and you would also find line dislocations, and you can even find screwed dislocation where the lattices are like basically just changing their orientation and things like that. So, the surface in general, what I want to say is basically much more heterogeneous in the atomic scale and not as atomically flat as we have basically just expected or said in the ideal situation. So, this is the surface that we are going to work. That means, whenever you are going to adsorb atoms onto the surface, you have to now come across these kind of surfaces where you have actually like variety of defects, kings, terraces, vacancies and so on. Well, in the next lecture we would try to adsorb atoms onto this in a real case, and then basically we have basically we can understand the situation a little better. Alright. So, now let me just try to adsorb atoms onto the surface, and this is basically can be understood as I have already showed you in the previous slide, that we have basically these monoatomic steps, kings, terraces, vacancies and so on. Now, when I adsorb atoms onto the surface, it is not just going to adsorb only onto the HCP, FCC and the top side, it is also going to adsorb onto the atomic steps, onto the kings and to the vacancy and so on. So, let me just show you how it really look like. So, this is a schematic of two surface layers. So, this is the first terrace, and this would be the second terrace. Yeah. So, these are the two different terraces, and now you can see basically if I would adsorb atoms. So, these are basically the add atoms that I am going to put onto the surface. So, they can get basically vacancies, they can get basically step edges, they can get kings, then they can get bridges and they can get HCP sites and so on. So, there are variety of adsorption sites that you can get on the surface compared to what we have seen the ideal cases just in the previous slides. So, now the question that you would ask, because we have already seen that depending on the site the adsorption energy is basically going to change, and we have already seen the hollow sites have the highest adsorption energy than the normal top site. So, now the point here I want to make, here in this variety of adsorption site, but if you take actually the vacancy, this is where the atom is basically going to get occupy the largest, because it has the highest coordination, because you can see here I have 6 atoms in the layer and 1 atom below. So, therefore, the coordination is basically 7 here, and if you take the king atom, this has a coordination of 6, the step edges has a coordination of 5, the HCP site has a coordination of 2 coordination, and this is having 3 coordination, and a top site have just 1 coordination. So, that means the adsorption energy you can see is basically increasing as a function of the number of coordination that the atom basically would get, right. And if that is the case, then you would find that this site, that means actually the vacancy site with the highest number of coordination is actually the one with the highest adsorption energy, and then the adsorption energy basically decreases as you go along to this. Yeah. So, just keep it in mind that these are the additional sites that we have just learned due to the fact that the surface is basically heterogeneous in nature, and then we are going to really work with this kind of heterogeneous surface in the next classes. Yeah, I thank you very much for the attention, and we meet in the next class with how to determine the adsorption energy. Thank you very much.